Hi. Hello, Internet. So, have you ever wondered how music visualization works? So you know how with some music players, when you play the music, you'll kind of see like dancing bar graphs or stuff that move to the music. I was kind of curious, and then when I looked into it, I realized it wasn't actually that complicated to implement. I just thought I'd share it. I thought that was pretty neat. Yeah, so if you're interested in how the FFT, like if you're interested in understanding more about the FFT, I think Veritasium has a pretty approachable and pretty good video explaining it. If you want something more technical, I think 3 Blue 1 Brown has a couple videos as well. But yeah, I mean, it's a big topic. There's a lot to dig into. So theory is one thing, but implementation is another, right? So I think like, especially if you're not used to this sort of thing, like the theory behind, the math behind FFT can be a little bit hairy to wrap your head around. But it turns out like you can implement the code in fairly few lines of code. Like this is it. This code I'm showing you, that this is the entire implementation I'm using. There are a few flavors of how to implement the FFT. I picked a pretty common flavor and approach. I saw a few online and then I tweaked it a little bit to fit my needs. But you'll note like there's not even any dynamic memory allocations here, right? It does use linear memory because I allocate these on the stack, but there's no need for any dynamic memory allocations. Does this work? Well, the first little program I wrote was just to like check that it worked. Just the values are what you expect. So I just checked it against some like known results online. So some simple values here. You'll notice that the results are pairs because the fast Fourier transform works on complex numbers. These looked correct, and I felt pretty okay about how well they would work. So now the fun part is like I want to create visuals, right? So my usual go-to for visuals, SDL2. Great. I mean, it's very simple. I'm just going to draw rectangles here. And then I also decided to include the mixer. The only thing I use the SDL2 mixer for is to read MP3 files so that, I can play them. And yeah, let me show you what that code looks like. So this is the first bit of code. All it does, so as you see, the SDL2 is included. The fast Fourier transform that you just saw, some, constants. So some details about how the FFT works. The kind of granularity we'll have is roughly 23.44 hertz. And then the maximum, with the given values, right? If we use 180, if we're only going to show 180 of the bins, the maximum is 4.2 kilohertz, which actually is large enough to cover the range of an 88 key piano, right? So the highest note on an 88 key piano, I think is like 44,100 something hertz. So yeah, even this, I was, as I started seeing it, it seemed like it might be a bit too much. It tends to be very left skewed. But yeah, those are kind of the choices I made. Some setup in main, load the music. Of course, we got to do that. PCM. So PCM will hold our raw audio data, right? And you'll notice that the PCM is always just float, but the buffer has to be a complex number, has to contain a vector of complex numbers because that's what the FFT works on. Okay, and then we got some like, the main loop here. Right. Chunk size. So here, if we have enough audio data, if we don't have enough audio data, we shouldn't, we just don't mess with anything. But if we do have enough audio data, we just draw the bunch of rectangles right on the screen. And that's about it. And then let's play some samples. Yeah. Anyway, I thought that's cool. You can see the individual notes, right? And you can see it moving. I don't know, that just makes me really happy. But I thought like, something that would be kind of cool to add to this is like, if you look at the height data, right, for each of the bar, we just take the absolute value of the corresponding component in the in the result of the FFT, right? So we're taking a complex number and then turning it into a floating point value. So we're losing some data here. I don't know what the best way to visualize this extra data would be, but I just thought it would be kind of like intuitive to like take the angle that the complex number forms in the real complex plane and then just kind of graph that as like a ratio of how far around the circle you go around. And then let's see that. So yeah, I don't know. I think it look. So I think it makes it look prettier. Sure. But so the last thing I wanted to share, instead of loading an MP3 file, I just figured why not just use a microphone to do it. I wonder if I should have just done that from the beginning. Then I wouldn't have to have had to bring the SCL mixer. But yeah, otherwise, pretty simple code, right? So roughly a little over 200 lines. Let's see what that gives us. Oh, let me try whistling, right? Ooh, very clear notes. Ooh, yeah, ain't that cool? I don't know. This is just way too fun. Ray, a drop of golden sun. Yeah. Oh my goodness. So that's that. So there's some thoughts here, right? Actually, an early thought I had while I was writing some of this code is like, music has a logarithmic scale, right? So when you go up an octave, you double the number of hertz, right? A440. If you want the next A note above that, it's 880, right? So like if you go an octave below, it's 220. If you go an octave above, it's 880. The difference is actually not constant. In fact, the difference is double what it was before, right? So like, wouldn't you want the graph to reflect that? As I was implementing this, and then I was like, I kind of like the original better. It just looks more fun and dynamic. And when I was looking around for how people were doing it, like I saw an article where like somebody was complaining, hey, so many people, they just show the raw FFT graph, but given how human hearing works, it's actually better to show the logarithmic version, right? And I was like, yeah, I totally agree with that. But I don't know. Maybe if I feel like it at some point, I'll share that version too. But yeah. So that wasn't, I kind of passed up on that one. Actually, I tried a second approach. So I was thinking like, okay, well, so one of the things that actually sucked about that was that the lower ranges, I just didn't have very much granularity in the lower ranges, right? Because each bucket interval is only 23.4 hertz. So in the lowest, when you go down to the really low notes, human hearing, I think it can hear like all the way down to 20 hertz or something. If you go down to 20 hertz, the next bucket is gonna be like, so you have 23.4 hertz, and then the next bucket is like 45 hertz or something, right? So there's a whole bunch of notes in there. Like that's a whole octave, right? You have 2 bars, and that's supposed to represent a whole octave. So it's not gonna be very good. And it just didn't look very good. It just looked like a fat bar on the left side. Another approach I tried was just like, I was wondering whether like this spread outness meant that the height of the bars would also be would be lessened. So I had some sort of I did kind of have some success with this in terms of like it looking nice, where I picked some constant value and then I made it so that like the height of each bar would be adjusted by some exponential rate as you go to the right. It looked okay. I kind of liked it, but it felt arbitrary because I couldn't, I couldn't immediately think of a nice base value to do that with. So I just had to tweak it, and I picked like 1.1 or something. Yeah. Anyway, yeah. So I just wanted to share that. I just thought it was very very neat. I just love little projects like this. Anyway, till next time, y'all.